to this point, we've only examined rate equations that were independent of temperature. And that's because all of the reactions that we observed thus far in this chapter have occurred at a constant temperature. Next, we'll examine the effect of temperature on rate. We see here that the rate constant of the rate law, which is given as K, is temperature dependent. The Arrhenius equation shows this relationship such that K is equal to A times e to the negative EA over RT. And the rate, as given previously, is given by some K times the concentration of the species in the reaction raised to the n power. So this is the K we're talking about. This K can be broken down further to be related to temperature by A times e to the negative EA over RT. And we're going to examine what each of these components means in just a minute. But T is the temperature in Kelvin, and R is the gas constant in energy units, which we studied previously, 8.314 joules per mole Kelvin. A is an entity called the frequency factor. This is the rate the reactant energy approaches the activation energy, and we'll see an example of what that means in just a minute. E sub A is the activation energy. This is the minimum energy needed to start the reaction or to overcome the energy barrier to the reaction. Here we see a reaction diagram where we have energy versus progress of reaction plotted. So reaction progress is on the x-axis and energy is on the y-axis. This is for the reaction where hydrogen and oxygen are forming water. Even though this reaction is thermodynamically favorable, meaning that we get some energy out when this reaction occurs, so it will generally go forward, we still have an activation energy barrier to overcome to go from starting material to products. And this activation energy is our E sub A in our previous equation. So the reactants have to begin to react together, and in order to do that, they have to overcome this activation energy barrier to move forward to form products. This activation energy is the amount of energy needed to convert reactants into the activated complex, which is at the top of that energy barrier and is also known as the transition state. The activated complex is a chemical species where we have partially broken bonds and partially formed bonds. So the bonds are breaking and the bonds are forming. And it's always high energy because of these partial bonds. Here we have another example reaction, the isomerization of methyl isonitrile. Here we have a methyl group attached to a nitrogen, which is triple bonded to a carbon. This is methyl isonitrile. If heat is added, this molecule can rearrange such that the carbon becomes connected to the methyl group and the nitrogen is now on the end. So it's just a rearrangement reaction. So it's a good one to examine when we're talking about this energy barrier. For this reaction to occur, the bond connecting this carbon, which is shown in black, to this nitrogen has to weaken. So the methyl, the carbon attached to the carbon that is the methyl group, is attached to the nitrogen, and this bond has to weaken and ultimately break, and a new carbon-carbon bond has to form. So this bond is going to break and this bond is going to form. So the nitrile group begins to rotate in order for this process to occur. So here we see an energy diagram for this process. So as the reaction begins, we just have our methyl isonitrile, and the nitrile group begins to rotate as we approach the activation barrier or activated complex, which is also known as the transition state. At that point, we have partial bonds, So the bonds are breaking and the bonds are also forming. So we're breaking this bond and we're forming this bond. This is called an activated complex. Then the molecule has to decide if it can overcome that activation energy, which it will do if it has enough energy, or it will go back and form starting materials. Of course, these molecules aren't really thinking, but if they have enough energy, they can overcome the energy barrier to form products. If not, they'll go back to starting materials. So the height of this energy barrier, which indicates how much energy is required to overcome that energy barrier, indicates how easy the reaction is for the starting materials to form products. So more energy would therefore lead to a slower reaction. If the energy going from starting materials to products is lower, so if the product energy is lower than the starting material energy, then our delta H will be negative, and that indicates that the reaction was exothermic and usually favorable. If the product energy is higher, then the delta H will be positive, indicating the reaction is endothermic and usually unfavorable, but not always. The frequency factor, which is given by the A in our K expression, is the number of molecules that begin to form the activated complex in a given period of time. So it indicates the approaches to the energy barrier. So for this reaction, the frequency factor represents the rate at which the NC part of the molecule wags, which means that it vibrates from side to side. Recall that K is given by A times e to the negative EA over RT. So this exponential factor, e to the negative EA over RT, is a number between 0 and 1. And this represents the fraction of reactant molecules with enough energy to make it over that energy barrier. The higher the energy barrier, the larger the activation energy, and the fewer molecules that have sufficient energy to overcome it. But here's where we can do something to change the rate. Increasing the temperature will increase the number of molecules with sufficient energy to overcome that energy barrier. And generally, increasing the temperature of a reaction increases the reaction rate for this reason. Here we see a thermal energy distribution plot. We see here that as the temperature increases along the x-axis, the fraction of molecules with enough energy to surmount the activation energy barrier also increases. The fraction of molecules is given on the y-axis. So we see that the number of molecules with enough energy to overcome the activation energy increases with increasing temperature. Next, we'll work some problems to help us understand the Arrhenius equation. The Arrhenius equation was given by K equals A times e to the negative EA over RT, where we see that K varies by temperature, and that's the K of our rate equation. If we rearrange the Arrhenius equation algebraically, we can use logarithmic rules to show that the ln of K is equal to negative EA over R times 1 over T plus ln of A. So what we get is an equation that takes the form of a line, y equals mx plus b, where negative EA over R is our slope. So negative EA over R is equal to m. And so we can say that EA, our activation energy, is equal to negative m times r. So we can get the activation energy from the slope of the line. So in this case, we see that we can plot 1 over the temperature, which is our x, and ln of K, which is our y, and that should give us a straight line. So R is the gas law constant in energy units, so the activation energy is given in joules, which is equal to R times negative R times the slope of the line.